Okay, everyone, I have a few updates for you, and then I'll let you get started in the next lab. We have the grades in our grade book for labs 1 and 2. We just haven't put them into Blackboard yet, so I'll get those in today. There was a quiz 3, I think it was last week. I was going to go over that real fast, and then lab 3 we'll assign that today. Okay, by the way, was there any issues with lab 2? I think everyone's got it. Everyone have that done?
Yeah, it was a nice lab.
Yes.
I forgot to take the quiz from the other week, and I meant to ask you in class the other day, but I forgot to.
Okay, just send me an email about it.
Okay, I sent you an email already, last week.
About the quiz?
Yeah, last Monday.
Okay. Okay, well, I can take it out of your calculation.
Oh, okay.
Okay, no problem. Okay, so let me go over quiz 3. I'll just get through this real fast, make sure everyone is on the same page, and then I'll introduce the next lab. Okay, so quiz 3 was about I²C. What's the result of one device pulling a wire to logic 0, another device pulling the same wire to logic 1? It's going to be, what, 0, right? 0? 0, right? What does a 1-bit signify in the RW slot? That means read, right? What's the value of the SCL wire when there are no transactions in progress? High. Yep. What's the result of 2 devices driving a single wire to logic 1 using a push-pull driver? 1. What's the result of one device driving a wire to logic 0, another device driving the same wire to logic 1? Yeah, it's a short circuit. Generally, I don't have a lot of experience with this. But my understanding is that if you do that, you'll get a voltage that's somewhere in between 0 and 1 in the forbidden zone. Okay. And then if you read that value, I think it'll probably read as a 1 because it'll be above 700 millivolts, which is the typical threshold for a transistor. So forbidden zone will, I think it'll be read as 1, but it's not a good idea to try that. What's the start signal? It's when you drive SDA low while SCL is high. And the stop signal is when you drive SDA high while SCL is high. How many times does control of SDA change during a single byte I²C read operation? Twice, because it changes control for the header acknowledge and the data acknowledge. Yeah. How many times does control of SDA change during a single byte I²C write? 3 times. Right? So you have to acknowledge the header, then you have to change back to send the data, and then you have to acknowledge the data. All right. What's happening in the following I²C? You have to figure out what the first and last 8 bits are, the header 8 bits and the data 8 bits. And then, of course, the read-write flag is 0, so you're doing a read, and so you're basically reading. And how can a collision between 2 I² I²C hosts be detected? This one is, I'm not sure if this is exactly how it works. This is just a possibility. But if I am trying to take control, take mastership, and I initiate a start bit, so I'm going to drive SDA low first, right?
Then you got to wait to see if something else is cycling the clock, because a host are the only thing that can cycle the clock.
Yeah, exactly. So I think the presumption here is that we have a collision, but I am the one that's slightly behind the other one. So if I'm behind the other one, if I'm lagging the other host that's trying to gain mastership, then there's a chance that when I pull SDA low during the first step of the start bit, the other host will be on the second step of the start bit, which means he'll be driving SCL low, right? And so I can detect that, and then I can back off knowing there's a collision, right? Now, if you start exactly at the same time, then this might not work. And I'm not sure exactly how you detect this. But as long as one host is slightly ahead of the other, this method, I think, will work. It seems reasonable anyway. On an I2C read, what side drives SCL? That would be the master. What is the limitation for adding additional devices to a single channel? Leakage current. I think the more devices you add, the more parallel resistors you'll have. Oh, and there's a limited number of I2C addresses.
Oh, yeah.
And the collision rate will increase because you'll have more contention on the bus. Master sees a 1 bit during the acknowledgement slot of a data phase. What does this mean? It means that the right address was received, but the data was not. At least that's one possible interpretation. And that's based on how there's an acknowledgement for both the header and the data. How many bit slots comprise a single I2C transaction, not including the start and stop? What is it? Bit slots, 8 and 8, but then there's the acknowledgement, so it's 9 plus 9, so 18. 18. Okay, any questions? All right. So today we're going to start the next lab. Lab sheet is posted, and that should be lab 3. Sorry. So the lab sheet is posted, and there's a typo with the due date on the submission box. I'll fix that. Okay, so as I mentioned at the beginning of the semester, all of these labs are inspired by a project we got online that balances a cube on one of its points. So each of these labs is exploring, most of these labs, not all of them, because in the next lab we have audio and LEDs that were not included as part of that. But this part of the project involves monitoring the battery voltage so we know how much charge we have left in the battery, right? So in order to do that, we are going to use the analog to digital converter that's available on the ESP32. It is a DC coupled analog digital converter, meaning that you can read DC values from it. Now, not all ADCs are like that. Some ADCs are AC coupled, which means you can only read an AC signal. Usually the faster ones are like that. But this is DC coupled, which is good because the battery is a DC voltage. It's also 12 bits, and it operates on the 3.3 volt supply. Now you might ask, isn't the ESP32 powered by USB? And isn't USB 5 volts? Yeah. I don't know why this is powered on 3.3 volts.
There's a voltage regulator on the board that regulates
Right.
the 5 down.
So the whole chip is just 3.3. Okay. Okay, so it's 3.3. The problem is that we are going to be using some very powerful motors to keep the cube balanced. I don't know where they came from. I think they're drone motors. I think they're designed for flight. And those motors are 12 volts. So we're going to have to put a 12 volt battery, which means we have to read a 12 volt, up to 12 volt voltage, which means the ADC, there's an issue there, right? So the way we're going to get around that is through a voltage divider that we have on the board. You'll notice if you look on there, there's a, the V battery is being dropped over a 33 kilo ohm and a 10 kilo ohm resistor that are in series. And then between those two, we have a line going out to pin 34 on the ESP32, which means that the voltage that we read is going to be multiplied by 10 over 43, 43 being 10 plus 33, right? So the total resistance here is 43 kilo ohms. And we are tapping it here above the 10 kilo ohms. So this is 10/43 times whatever the voltage is on VBAT. Okay, so that should get us into a range that we can read between 0 and 3.3, right? So now the battery is nominally 12 volts, but we want to be able to read up to 14.2 volts. Okay, so we're trying to read a value between 0 and 14.2, but it's being interpreted at the pin as 0 to 3.3. right, through this voltage divider. Okay? Now, one thing I want to mention is the VBAT input is intended to be hooked up to the power supply with a clamp, a alligator clip clamp, which Alex has passed out. Did you pass those out? Yeah. Okay.
If anyone doesn't have one, let me know and I'll give one for you.
Okay, but there was a bit of an oversight here because right next to the VBAT terminal is something called V 5 volt DC. And the 5 volt DC is shorted to the 5 volt supply on ESP32, which is probably also shorted to your computer through the USB connection, I'm guessing, right? Which means that if you misplace the alligator clip by 2 millimeters or so, you'll cook not only the board, but possibly the computer as well. So you want to be careful with that. So make sure that you clip to the VBAT. The VBAT is the high voltage, and the 5 volt is the 5 volt voltage, and the ground is shared by both. Both power supplies share the same ground. They're both coupled through their ground, okay?
No, I don't.
I'm just going to electrical take this right here and not have to ever worry about that.
Yeah. Yeah. Now you may wonder why the 5 volt is even there at all if we get power through the power supply, through the USB. I'm not sure.
Delivering enough current at 5 volts, or if it is, you got to shove a lot of current to drive those motors.
Yeah, well, that's through the 12 volt though. The
okay.
5 volt is kind of redundant, I think, right? That's just if you want to use it without USB, right?
Yeah.
Yeah.
We're not using that right now.
Okay, so we're not. So in other words, just to clarify, do not use the 5 volt supply. Don't connect to the 5 volt supply. Connect to the VBAT. Okay. In hindsight, we should have either not had the 5 volt supply or put it on like the other side of the board or something. Okay. Any questions about that? Everyone comfortable with the voltage divider? So in other words, if you want to know what the VBAT input is, you have to do the ADC and then multiply that by 43/10 in order to convert it back into the original voltage range. Okay. All right. So now here's the other issue. The ADC on the ESP32 is basically garbage. It doesn't work very well at all.
Okay.
And the reason I say that is because this plot plots the voltage that you read on the horizontal axis and the actual voltage on the vertical axis, which means that if you look at the vertical axis, if you look between 0 and 100 millivolts, you'll notice that the value read it goes straight up from 0. So this blue line is the voltage that we are reading, right? And this blue line goes straight up. It stays on the vertical axis from 0 until 100 millivolts, which means that anything that's less than 100, any input voltage less than 100 millivolts will be interpreted as 0 volts by the ADC. Okay? And then once you get past 100 millivolts, so between this dotted line on the vertical axis up to this dotted line on the vertical axis, which is roughly 2.8 or so volts. So from 100 millivolts to 2.8 volts, the voltage you read is going to be less than the voltage, greater than the actual voltage, right? So it's going to overestimate the voltage between 100 millivolts and 2.3 volts, right? Okay, then between 2.3 volts and 3 volts, it will underestimate the voltage you read. And then above 3 volts, it's just going to max out. So any voltage greater than 3 will be read as 3.3. So if the input voltage is 3 to 3.3, the ADC will just estimate 3, I believe, right? Because this line goes straight up. Make sense? Make sense? You guys with me? Okay, so this dotted line is a linear, this is the identity. And so ideally, the behavior would match this dotted line, but it doesn't. It matches this blue line, which means it's overestimating here, it's underestimating here, and then there's these two regions at the beginning and end where it kind of saturates.
Okay. So that means when it's fully charged, we're not really going to see any depletion until it's like at 90%.
Yep. Yeah, exactly.
That's sort of how crap cell phones work.
Yep. Okay, but the good news is that we can calibrate at least above 100 millivolts and below 3 volts. In that region, we can automatically calibrate the ADC using code and through a calibration procedure. So this gives us an excuse to communicate with the power supplies. So the power supplies, obviously you turn them on, you use the buttons on the front panel to set them up, but you can also set them up through a serial interface on the back. And luckily for us, we have 2 spare serial interfaces on the ESP32. We're only using one of them for the console. We got 2 spares. And so you'll notice on the board there is a DB9 connector. DB9 is the old 1980s, 1990s serial connector. It's got 9 pins. It looks like a trapezoid, an inverted trapezoid. So if you plug in the cable in there on the board and plug the other end into the power supply, we can take control. We can have the code running on ESP32 take control of the power supply and program the power supply to put out a known voltage, and that gives us a ground truth. So in other words, we can then map the actual voltage as we know what it is based on our instructions to the power supply. Then we can read the ADC value, which will be different than whatever the power supply is putting out, except for maybe, yeah, it's generally going to be different. And then we can build a model of the power supply internally in the code. We can construct a model that will correct the voltage we read and hopefully give us an accurate reading. Does that make sense?
And this code should translate over to an actual battery.
Yes, yeah. Yeah, it should work. So in theory, it should work on a battery as well. Yeah, because the power supply is, we're using that as a surrogate for the battery. Originally we meant to plug the boards themselves in the back of the power supply without having a cable, but then what happened with that? We couldn't get the right connector, right?
So the connectors, they have the wrong, the little screwy things, the little things on the sides. They were the wrong polarity, so they hit the ones on the power supply, and you can't. Well, originally I thought you couldn't unscrew them because it would cause the faceplate of the connector to fall off, but it turns out the ones that we actually use on the final design, that doesn't happen. You can unscrew them and the face of the connector does not fall off. So you can actually plug these into the power supply.
If you take the screws. Okay.
If you get a nut driver.
Exactly. Yeah, exactly. So if you can unscrew those, but the problem is the connector's in the back, right?
Yeah, it's in the back.
That sounds like a really fun way to break
It's a little annoying to have.
Yeah.
It's easier to use cable for sure.
So we bought the cable. So Alex gave you all cable. So you need the serial cable and you need the banana clip, alligator clip cable. So one of the cables goes in the back of the power supply and the other one goes in the front. Okay. Okay. Now the power supplies, the strange thing about them is that the control of the power supplies is mutually exclusive. You can only control them from the buttons or from the serial port, but not at the same time. So you have to put them into a mode where they're controlled via serial port. And then once you do that, it locks out the front panel. Now, if you panic and you have a bug in your code, I think you could just turn the power supply off, and when it comes back on, it'll be back in front panel mode, right? So it's not like you're going to permanently brick the power supplies this way, right? Because I think the power button still works even if they're controlled by the serial port, right?
Yeah,
and if all else fails, just unplug them from the...
These are hard toggle switches, right?
Yeah.
Hard power, so it'll actually.
Yeah. Okay, so how does this work? So I have a list of commands here, and this is not an exhaustive list, but we have a link on the lab sheet to the manual for the power supply, which has an exhaustive list, right? These are just some of the commands. These are the only ones you need, though. So you have to, begin by, well, there's actually, well, first of all, let me back up here. So first of all, we want to initialize serial 2, right? So you want to say serial 2.begin. You can put this in your setup function. And you have to set it to 9600 baud and set it up for 8 data bits, 1 stop bit, which I think is the default. But then you have to set the 2 pins that we're using for transmit and receive, right? So that's pin 2319. And then once you have that done, then you can just type serial2.print, and you can send commands to the scope. Each command needs to be terminated with a carriage return new line. Carriage return is \r, new line is \n. And by carriage, I mean typewriter carriage, like the typewriter. They're using typewriter stuff. This is literally a typewriter, move the typewriter thing to the left and then go to the next line. I have no idea why we're doing typewriter stuff, but that's just, you have to do \r, \n, right? Okay, so that, make sure that comes after every command. There is a command that you have to do initially to establish the connection. That's in the lab sheet. Once you establish the connection, you can basically use these commands to select a channel. These power supplies have 3 separate independent channels. 1, 2, 3. I mean, most people just use 1, but that depends on which connector you plug the banana clips into.
By the way, you cannot use channel 3 because its voltage range is different from the other 2, but you can use either channel 1 or channel 2.
It doesn't go past
No, I think
5
it's
volts.
5.
5 volts. Okay, yeah. So use channel 1 or 2, and then you can set the voltage or you can set the current limit. You can enable the output. Remember that normally these supplies are by default, they're not putting a voltage out. You have to actually enable the output to have them start outputting a voltage. So there's a command for that. There's a one that enables or disables all 3 channels. You probably won't use that command. There's a beep command that'll cause it to beep. You don't need to use that for the lab. There's also a command that'll display a text string on the front panel, which is kind of cool. But again, you don't need that for the lab. It's not required. And then there's a command to clear the text if you put text. So the only ones here that you really need are setting the voltage and enabling the output. Oh, and you probably want to set the current limit to what it was, 100 millivolts? Milliamps rather?
I haven't bothered setting the current one.
Okay, I think the default is 100 milliamps. Yeah, this is the first time we've done this lab, so we don't have a lot of experience with this yet. Any questions about that?
Yeah, by default, does the display still output, even if you're controlling it from the back, does it still output the voltage?
I believe so, right, yeah. The problem with these power supplies is when you set the voltage, it shows you what voltage you set it at for about a second, and then it clears it to 0. And the reason it's 0 is because the voltage would be, typically you set the voltage when it's not actually on, right? So you set the voltage, you say like 5 volts or 12 volts, and you hit enter, and then it's like, okay, and then it says 0. And then once you hit the on button, then it'll show you the 12 volts, right? Because it's actually putting out 12 volts, right? So it's a little bit, I find these a little confusing for that reason, right? Can you set the voltage when it's on, or you have to turn off to change the voltage?
You can set it. That's what when I have my code stepping through them all, I don't have it turn it off in between because that would take a lot of time. I just leave it on and step it through while it's
Okay,
You can change it while it's on, even from the front buttons.
Okay. Okay. Any questions about that?
One other thing I should note as well, there's a chance that people who have used these power supplies in the past have set the voltages to like crazy values. So before you connect your board to the power supply, turn it on and make sure the voltages are like all set to 0. Because
Or something
the
not
previous
insane.
user could have set them to like anything as a 30 volts, and we can't tolerate anything over like 14 volts.
This one's
So,
0, so.
Yeah, like mine was set to 16 volts when I first turned it on here. So just make sure of that before you plug in your board. And you have to hit the on off button in order to actually see what they're set to.
Oh,
Yeah, that was, yeah, that's what I was saying before, is that when they're
This one's set to 18 volts on channel 2.
Yeah, that's what I'm talking about. Like zero all those out just to be safe.
All right.
Because if anyone needs help zeroing them out, I can help with that.
Okay, so just to be clear, when you turn it on, it's going to say 0.
Yeah.
When you turn the power supply on, not the outputs. When you turn the power supply on, it comes up as 0. If you want to see what it's set at, you actually have to turn the outputs on, right?
Right.
That's a terrible design.
I know.
That is really bad.
Really
That's just awful that you have to energize the outputs in order to see the setting. Okay, any questions about that? Okay, so moving along. So how do we create a model? How do we create a calibration model for the scope?
Ooh, I don't like it.
Well,
Oh, it's not that bad.
I'm not sure if this is the best way. This is what we've come up with. So the idea is to create a piecewise linear model, which means that you do a linear fit.
Okay.
Right? A linear fit is f of x equals mx plus b. You remember mx plus b from middle school? So m is the slope of the line and b is the intercept. Okay? The problem is, though, is that you don't want to create one linear fit for the entire range, because then, basically, then you have something that would look like this. You'd have one linear line like this dotted one, and you would get it as close as you can to the blue line, but you would be limited on how much you can match, because the blue line's not linear, right? So it would be very inaccurate, in this up here, right? For instance, you might be able to fit a linear function pretty close to this part, right? But it wouldn't be very good at the two ends. So that's where the piecewise part comes in. Piecewise linear is where it's a very simple hack. You just divide up the x value, the range of x values, into what they call pieces or ranges, which, they can be equal size ranges or not. They don't need to be. Sometimes when you're trying to do this with an exponential function, you actually have the ranges are logarithmic, right? But in this case, we're going to divide the ranges of x into equal size segments. So here's an example. So this is just a generic example I wrote when I was testing my code for this. So in this case, x ranges from 0 to 10, and I've divided the range of x values into five pieces, right? 1, 2, 3, 4, 5, right? Each one of those 5 pieces has its own linear fit, and I fitted according to these little circles are the data points I read, right? So each one of these lines is fitted to the data points that are in each one of those 5 pieces, each one of those 5 ranges, ranges of x. And so you can see that this looks like this is actually an exponential function. I added noise to it to create each one of these samples. And so this line, you look at this and you're like, oh, that looks like a pretty good non-linear, exponential, but it is linear. It's just divided into linear segments, right? It's kind of built up from individual linear segments, right? And so that's what we want to do for this lab is we want to, in fact, in this case, so we want to do 16 segments. So we're going to take the voltage from 0 to 14.2 volts, 0 to 3.3 volts, right, which is what we're reading. 0 to 3.3 volts, and we want to divide it into 16 equal size ranges, and then we're going to do a linear, what they call a simple linear regression for each of those 16 ranges. And to do the linear regression, it's really easy. You just have to read a bunch of x's and f of x's. Right, now remember, we have ground truth now because we're controlling the power supply. So x would be the voltage we read, right? That's the garbage misreading from our ADC. And f of x is the ground truth, the actual voltage, right? And so we want to train a function, f of x, to translate what we read into what the truth is, right? So if you read a bunch of x's and f of x pairs, then you'll have a bunch of x and y's, x sub I, y sub y, x sub I, y sub I, right? So you'll have a bunch of x, y pairs, and then all you have to do is come up with 16 values of m, which is the slope, and 16 values of b, which is your intercepts. And there's just a closed form equation for each one of those. You just have to, these are the 2 equations. So you've got a bunch of x and y's, and you just plug them in here, right? and to get the slope and intercept, right? Now, how many X and Y's are we going to have? How many samples are we going to read? Well, that's up to, that's kind of up for debate. When Alex first did this, he sampled every 10 millivolts on the power supply, right? Which meant that he had to do 142, no, more than that, 1,400, yeah. So it was, so there's,
It took a while.
yeah, it's about 1,500 adjustments to the power supply to sample all the X and Y's. I hope that's overkill, because that would take an hour or more.
I just tried the 50 millivolts and it seems to be fine.
Okay. Well, so then later I thought, well, let's do 100 millivolts, because that would just be 142 readings. And then the problem, though, is keep in mind that, the 100 millivolts is kind of a magic number here, because that's pretty much anything below 100 millivolts is going to read as 0. And also the upper end here is what I say it was. Anything over 3 or so is read as 3.3. Okay, so I think, so we compromised here, and in the lab sheet it says 50 millivolts. But that should be something you can change in your code pretty easy, right? Make sense? So I would just have that as a variable. So you're going to walk the power supply through the whole range in 50 millivolt increments, which will give you roughly 300 measurement points or so, about 300 measurement points. And then each one of these slope and intercepts will be 1/16 of that, right? So you'll have about 300, so there'll be 300 divided by 16, right? So maybe around 20. You'll have about 20 X and Y's that are used to calculate each of the 16 slopes and intercepts, right? Does that make sense? So then once you walk through those ranges, then you tell the power supply to start paying attention to the front panel controls, right? You release control of the power supply, and then when you demo your project, we can go up and we can make adjustments on the power supply, and then your console will print its interpreted value, right? And then we can figure out how accurate your code is. Because if I dial the power supply to say 5 volts, I'm going to look at your console, and hopefully it'll say something around 5 volts, right? Because your calibration model will be correcting it.
This calibration is something you would only run the first time you get your new
Right.
supply, be it a new battery or a new.
Yeah. So the way it's worded in the lab sheet, every single time you run your code, it's going to run through that. But of course, if you want, you can make it a little bit more robust than that. You could have the user type a command or something to put it into calibration. But I'm fine with that. I don't care. You don't have to have it run through the whole calibration every time you boot, right? Boot up the board. Make sense? So I have some example. So there's like basically you'll be in calibration mode first, and then you'll build your calibrated model. Actually, you could probably build it as you're in calibration mode. You can do it. You can build it online, right? Because you're going to be calculating the equation as you go. And then enter monitor mode after that, and then just display. Your monitoring mode is just monitoring the voltage and printing it out. Okay, so here's an example for an output. So so this is what you'd see in your console. Entering auto calibration mode, please wait. Taking control of power supply, success. Auto calibrating, you could print a little, percentage complete. Of course, you don't need, you'll see the voltage on the power supply. You'll have an idea of how far along you are by looking at the power supply, right? You can see that on the display. But you can also print a message here, and then entering monitoring mode, and then every second it'll print raw voltage, and then you can print the raw value from the ADC. So the ADC is, you're reading an integer from that, obviously. So, and you're having to interpret this as a raw voltage and then a corrected voltage. Oh, I have a typo. That should say voltage, not voltage. But anyway, raw voltage 2.34 volts, which is interpreted from an ADC reading of 2904, and then corrected voltage 2.54 volts. And then there's a second correction you have to do to compensate for the voltage divider, which is where you multiply this by 43 over 10. So for example, you may read 2.34 volts, correct it to 2.54 volts, and then interpret that as an 11.18 volt from the power supply, right? Before the voltage divider. Make sense? So there's 4 pieces of information: raw voltage, raw ADC, corrected voltage, and then power supply voltage, right? Estimated power supply voltage. And then you can just print that every 1 minute. Okay, so the idea is that this will allow us to, presumably as the battery capacity as the battery is discharged, the voltage will start to dip, and then we can estimate the battery charge with this. Hopefully.
Oh,
That's the idea.
I'd like to note about the stepping through the voltages. This might be obvious to some of you, but I just want to point it out anyway. When you're stepping through all the voltages, make sure to put a delay in your code in between each step, because the power supply cannot respond immediately. So put like a 500 millisecond delay each time you step it, so it has time for the voltage to stabilize before you
Delay. Okay.
Yeah, there's no way to ask the power supply if it's done, right? So you're having to do this asynchronously. There's no.
500 milliseconds would be a good
Half a second.
place. Yeah, about half a second.
Okay.
You can go longer if you want, but I just wait.
You'll have to experiment then, because there's no way to handshake with the power supply and synchronize. It would be nice if the power supply would acknowledge when it's finished changing, but it doesn't do that, right? Or are you pretty sure? Okay. Okay, yeah, so you'll have to put a delay in after you change the voltage. So half a second, and then there's, what do we say, 300?
Roughly, yeah.
So it's going to take about 2 minutes. So we're looking at about 2.5 minutes for this process to complete at 500 milliseconds per.
For the
Yeah.
sake of testing, you could, take fewer steps. Just-
Oh, sorry, that was for 50 millivolt step. It's going to be 300.
Yeah.
So we're looking at 5 minutes. It should take about 5 minutes to do the calibration then, right? At 50 millivolts and 500 milliseconds,
Makes sense.
right?
But wouldn't you divide that by 2, though? Because it's 500.
If it were 100 millivolts, it'd be about 150 steps, right? And you'd have to double that at 50 millivolts, so 300 steps. And and then divide it, because the 5 half a second. You're right. Yeah. So 100. Yeah. So it is about 2 minutes. That's right. Yeah, about 2 minutes or so. Okay. Any questions? All right. Great. Well, so we've got this one due in 2 weeks. Hopefully, it'll be enough time for this one. Let me know if you have any questions.